All right, we're going to take a look at more sampling distributions now. So we're going to do the sampling distribution of the sample mean. So we've already looked at the sampling distribution of the sample proportion. And now again, we're going to be looking at not groups of things and taking the proportion, but taking the average. Okay. This is all some review here. The method we're going to employ is probability, expected value, and variance. So we're going to start with the roll of 1 and 2 dice. Okay. So here's the idea. We are rolling a fair die, and a fair die is simply one where each probability is equal. And the random variable is the number of spots on any throw. Right now it sounds like a binomial. It's not going to be a binomial at the end of the day, but you'll see. So the probability distribution for getting a particular value is 1/6 all the way around. We can calculate the mean at 3.5. And the standard deviation will be 1.71. Take a look, the variance here is 2.92. That's going to come in to play in a few minutes here. Okay, so the mean, the variance, the standard deviation of the roll of a die 6 times. Okay, now here's the distribution if I take 2 die rolls and I average the 2 together. Okay, so the first one here, if I go back, was an individual die roll. Okay, I have a 1/6 probability of any particular outcome. Now I have 36 different possible outcomes. Okay, now they're not all the same. You can see that you can get an average of 2 by rolling a 1 and a 3, and also by rolling a 2 and a 2. Okay, and what we're looking at here is simply we're going to roll a 1 and a 1. That's an average of 1. A 1 and a 2, it's an average of 1.5, and so on and so forth. You can see how these work out. So we're looking at the distribution of averages now, the distribution of means. So there are 36 possible samples of size 2. There are only 11 values for x bar, okay, and some occur more frequently than others. Okay. So here's what we look at. Now we have a new distribution. It's kind of a pyramidal kind of distribution here. And you can see that the chance of getting a 1, an average of 1 on 2 rolls is 1/36. The chance of getting a 3.5, again, I'll highlight here, is going to be 6 out of 36. And again, we're keeping it in 36th, so we don't have to reduce or anything like that. The chance of getting a 5, for instance, on an average of 2 rolls, there are 3 ways to get an average of 5. 3 ways out of 36 possibilities. So now we're looking at what's the distribution of averages of 2 rolls. Well, we can see again that the average appears to be 3.5. Okay, but you'll notice the standard deviation has gone down to 1.21. Okay, and the variance has gone down to 1.46. So the variance has gone down by a factor, and therefore the standard deviation has gone down by a factor. Okay, because you see it's more common now. It's less common to get a 1 or a 6 with 2 rolls, okay, than it was with an individual roll. It's common sense at this point. Okay. Well, here are the 2 distributions. Here's my first distribution. Chance of rolling 1, 2, 3, 4, 5, or 6 are all equal to 1/6. But the chance of rolling 1, 2, 3, 4, all the way up to 6, so there have values allowed here, is going to be less chance of rolling a 1, less chance of rolling a 6, more chance of rolling a 3.5, relatively speaking. So the average of both distributions is still 3.5. And the standard deviation is gone down by a factor of square root of 2. In particular, the variance, if we look back at the variance of the first, the variance here was 2.92. Remember I said take a look at that. And the variance of the new distribution is half that, 1.46. Okay. So when I roll 1 die, the average is still 3.5. When I roll 2 dice and take the average, the standard deviation goes down by a factor of the square root of 2. The mean stays in the same place. Okay. So the mean of the sampling distribution of size 2, when I rolled 2 dice and average them, is the same as the mean of the original distribution of rolling 1 die. The variance of the original distribution, of the new distribution where I rolled 2 dice, is the same as the original distribution divided by a factor of 2. So this is the new distribution, the average of rolling 2 dice, the original distribution here and here, what happens if I roll 1 die at a time. So what's neat about this is that no matter how many dice I roll, I could roll 15 dice and take the average of those and compare all the different possible averages of 15. If I do that, I'm still going to expect on average a 3.5. Right? I'm still going to expect a 3.5 on average in my sample. However, the samples are going to vary from sample to sample by much, much less. And as a matter of fact, the variance is going to go down by a factor of n. So that's to say, if I roll 3 dice, I'm going to take the original variance and divide it by 3. What that means is that the standard deviation, the new standard deviation, ends up being the same as the old standard deviation divided by square root of the sample size. Okay, so here this brings us to the central limit theorem, which is probably the most important theorem we're going to look at. The central limit theorem says that, well, what's this shape? It talks about the shape. As long as the sample size is large, so 2 is not big enough, 3 is not big enough, but once we get really quite big, we're looking at groups of dice or whatever we're looking at, and the groups are large, then the sampling distribution of the sample mean is approximately normal. Okay. The larger the sample size, the more normal it looks. Okay, so if I were dealing with 40 or 50 dice at a time rather than 2 dice at a time, that shape would no longer be like a pyramid, like it was here. That shape would look very much like a normal curve, enough for us to use the normal distribution. Okay, so here's the central limit theorem again restated. The sampling distribution of the sample mean will be approximately normal as the sample size increases. The mean will be the same as the original mean, and the standard deviation will be the same as the original standard deviation divided by the square root of the sample size. This works typically when the sample size is at least 30. Okay, so for instance, with the sample size of 2 dice, it doesn't really work for us. The mean and the standard deviation will still work, but the distribution will not necessarily be normal. Once I start getting above groups of about 30 dice, okay, once I start looking at this region, then the shape of my distribution will be normal, or pretty normal. Okay. One thing important to note down here is that if the original distribution is normal, now remember the original distribution of dice was uniform, it was straight across, but if for some reason I have an original distribution that was normal, then the sampling distribution of x bar is automatically normal. We don't need a big sample size. So if we start with a normal distribution and we take samples out of the normal distribution, the new distribution is already normal no matter how big the sample is we take out of the original distribution. All right, let's look at an example. We have the foreman of a bottling plant, and he's observing the amount of soda in a 32-ounce bottle. He notices that the amount of soda bottle to bottle to bottle is normally distributed with a mean of 32.2 and a standard deviation of 0.3. So we have normal, mean of 32.2, standard deviation of 3. If a customer buys a bottle, what is the probability the bottle will contain more than 32 ounces? Remember, 32 is what's advertised, but they always overfill it by a little bit. This is a plain old normal probability. Here's 32.2. Oh, pardon me. 32. Can't seem to draw. 0.2. Standard deviation of 0.2. So we're going to go 32.4. Oh, 32.5. And 31.9 is right there. Okay, so one standard deviation to the left, one to the right. We're looking right about there. So we want this area. It should be bigger than 50%. I'm looking for the probability that the amount in the bottle is bigger than or equal to 32 if the mean of the distribution is 32.2 and the standard deviation is 3 and the distribution is normal. Again, I can go back to my calculator and do this very quickly. And we're going to use the shortcut that we've been talking about a little bit, where I go to second vars, normal CDF, and I put in the lower number being 32 to infinity. My mean is 32.2. My standard deviation is 0.3. I expect this to be about 0.747. Here's the same thing here. All right. So x is normally distributed, mean of 32.2, standard deviation of 0.3. We're looking for the chance that x is bigger than 32. If you'd done it with a z-score, you could have done a z-score of negative 0.67 and found the probability is 0.7468. Just the same thing we've been doing. There's about a 75% chance that a single bottle of soda contains more than 32 ounces. Here's part B. Here's the part where we get into the sampling distribution. The foreman now is interested in, well, what about a 4-pack? They sell bottles in 4-packs, this particular place. So he's noticed again the same kind of thing, bottle to bottle. This is the average. This is the standard deviation. Still a normal distribution. Now, if the customer buys a carton of 4 bottles at a time, what is the probability that the mean amount in the 4 bottles will be greater than 32 ounces? Okay. So, we want to find the chance now that the average is 32 or bigger. Not the individual bottle, but the average of 4 bottles is 32 or bigger. So now we're talking about a sampling distribution. The distribution is not individuals. It's a distribution of samples. All the samples are size 4. Okay. So the central limit theorem says that if my sample size is really big, I can use a normal distribution on the sampling distribution. The second part says this, that my original distribution is already normal, then we don't need a big sample size. Here, the original distribution is already normal, so we don't need n, which in this case is 4, we don't need n to be large. Okay. We know also that since this is a sampling distribution by the central limit theorem, the mean of the sampling distribution, so the average we should expect in a 4-pack, is the same as the average we should expect bottle to bottle. We also know, since this is a sampling distribution of the sample mean, that the standard deviation of 4-pack to 4-pack to 4-pack, the variability among 4-packs, is the same as the variability among bottle to bottle divided by a square root of the sample size. So in this case, it's going to be 0.3, which is the bottle to bottle variability, divided by the square root of 4, which is 2, which brings us to a variability of 0.15 ounces. Okay, so we're looking for the chance that x bar is bigger than 32, and now we do the same thing. Instead of a z-score of negative 0.67 as we had before, we end up with a z-score of negative 1.33. And again, if we go back to normal CDF, and we do this same thing, but now we're going to do it with the new standard deviation, because that's really the only thing that's changed. The variability about 4-pack to 4-pack is different. Now we get 0.9082, which says that there's a 91% chance that the average of a 4-pack will exceed 32 ounces. So bottle to bottle to bottle, okay, we expect there's about a 75% chance that bottle to bottle to bottle will, a particular bottle will be overfilled, but there's about a 91% chance that the average of 4 bottles will be overfilled. That's the idea of a sampling distribution. Not comparing bottle to bottle, but 4-pack to 4-pack. Okay, that'll do it for now. See you guys next time.